Okay, welcome to the proof of line 4. Today we'll look at line number 4 from policy gradient proof. Here it is in the context of the previous line. As you can see, this is what we have to prove. So let's go over what we are after here. So on the left-hand side, this part here, and on the right-hand side, this part here. So what we want to do here is get rid of the rewards in the sum here, so that right-hand side has no summation over the rewards, right? And that there is no rewards in this dynamics function. And there is no rewards in this sum here. So we only have the gradient of v. So basically trying to get rid of the r in the right-hand side completely. So let's start with the previous line 3 that we proved before. This is what we have. So let's split the summation here that goes over s prime and r into the two sums, s prime and r. This is equivalent because this is actually just a shorthand for that. Now, let's distribute p over r and v. In other words, we'll take this dynamics function p, multiply it by r, and multiply it by v. So we have p times r plus p times v. Pretty simple so far. So what we want to do next is apply the product rule to this sum over here. And the product rule is simply the gradient of the first term in this product times the second term plus, so gradient of p times r, plus this term p times gradient of r, so p times gradient of r. And then we just sum the next term here, which is gradient of p times v, gradient of p times v, and then we take the first term here and multiply it by gradient of the second term. This is the product rule applied just to this inner sum here. And a lot of things go to 0 because the dynamics function p does not depend on parameter theta. Remember, this is a gradient with respect to theta. And clearly the dynamics, the world around us, does not depend on which policy we're using. It's going to tell us where it's transitioning regardless. Whether I'm using a human to lift a rock or a robot to lift a rock, the physics don't change. So this goes to 0. Now, gradient of r goes to 0 because that's a constant. And gradient of this dynamics function also goes to 0 for the same reason as before. So the only term we have left is gradient of v s prime following policy pi. Why does this not disappear? Well, because the value function is dependent on policy pi. So if you use one policy, the value of a given state will be different than if you use a different policy. And clearly, our policies is conditioned on theta, parameterized by theta. Okay, let's move up what we have so far. So after canceling all the terms, we have only the term with the gradient of v remaining. Let's rewrite this part here by applying the product rule, and you can see all we have is this last term here. So two sums of p times gradient of v. So you can see that this gradient kind of went inside there. All these terms canceled out, and we have just this one nice little term remaining. So now we can take the gradient v term out of this summation over r, because clearly gradient of v pi s prime has no rewards in it, no r terms there. So we can just move this into an outer sum, leaving inside the inner sum just the dynamics function. All right, so now let's move up what we have so far. And what we want to do now is get rid of this summation over r. So what do I mean by that? Well, I want to have this whole thing not be a sum, but just a dynamics function in terms of s prime, s, and a. So to get rid of this summation over r, we're going to use this equation 3.4, which is basically the marginal distribution. But to explain it a bit further, what we have is the dynamics function here expressed in terms of s prime, s, and a only, meaning that if we start in some state at previous time step s and take some action a and end up in s prime, that is equal to this more general dynamics function, which is probability distribution over s prime and r given s and a, where we sum out the r. So intuitively what this means is we basically start in some state S and we go to state S prime and we get some reward. Now there is multiple possibilities of different rewards we can get. So we can go to S prime and get reward 1, we can go to S prime and get reward R2, we can go to S prime and get reward 3. So just in that single S prime state, we can probabilistically get different rewards. So what we can do is we can just sum the probabilities over those rewards, so that all we get is just what's the probability of going to state S prime, and then regardless of which reward we get, we don't care. Essentially, we just care about the probability of ending up in S prime. And so this is what this equation 3.4 represents. All right, now let's apply this equation 3.4 to this term here. So it's just pretty straightforward application where we just replace this term with dynamics function that only involves S prime, S, and A. And you can see we got rid of the summation over R, and all we have is P S prime given SA. Finally, let's rearrange these two things, just switch places here. First, we'll have dynamics function P times the gradient of V S prime. All right, and this is exactly what we had to prove. We now have completed line 4. So this is going much slower than I expected, and we're not even to the hard stuff. So enjoy the rest of your day and see you next time.